dear students at home, how are all of you? I hope you're all doing great. And I welcome you to today's class. I still remain your chemistry teacher, Auntie Chidera. Today we'll be looking at chemistry for SS2 students with the topic hydrocarbons. And by the end of the lesson, the students should be able to define the term hydrocarbons, explain the classifications of hydrocarbons, define certain terms of hydrocarbons like the homologous series, functional groups, and all that, and also describe and explain all that has to do with isomerism. That is for hydrocarbons. Now, looking at the topic hydrocarbons, this actually refers back to the periodic table. Now, what is the periodic table? The periodic table is actually a table that shows the classification of elements or the arrangement of elements in order of their increasing atomic numbers, hydrogen, helium, lithium, beryllium, boron, and all of that. These are the first 20 elements. Now let's look at hydrocarbons. Hydro, referring to hydrogen, and carbon. Both of them are actually elements in the periodic table. Now we talk about hydrocarbon. Just the name should tell us that it's actually a combination of hydrogen and carbon. But hydrocarbons actually is a part of, or rather, belongs to a branch of chemistry that deals with organic chemistry. Of course, we have so many branches in chemistry: organic, inorganic. We have the physical chemistry, environmental chemistry, and all that. So, hydrocarbons deals with organic chemistry as a branch of chemistry. Now, what is organic chemistry? Organic chemistry actually refers to the study of carbon and its compounds. Carbon and its compounds, with the exception of, we have the oxides, the sulfides, triazocarbonates, the nitrates, and trioxide, triazosulfate, triazocarbonate, and tetraoxosulfate, and all of that. Now, when we talk about organic chemistry, we're talking about carbon. Carbon is the central element that we are dealing with. Carbon. And of course, carbon has an atomic number of 6. Hydrogen, helium, lithium, beryllium. You can't for yourself, you find that it has an atomic number of 6. Now, this will give a structure of carbon to be something like this. Carbon is 6. We have 1, 2, 3, 4, or rather, let's do it here. 3, 4, 5, 6. So, carbon has 4 electrons in the atmosphere. And because of the fact that it has these 4 electrons, all of them needs other compounds or other elements to bond with it. That is why the bonding of carbon is really big. And when you bring up all of these compounds that carbon forms, because of this nature of having 4 electrons in the atmosphere, because of this nature, it has very big branches and all of that. That is why it contains a particular branch in chemistry. That is the organic chemistry. Now, with this particular one, carbon actually can combine with other elements. Of course, if you combine with chlorine to give us the tetrachloromethane, 1 chlorine, 1 chlorine, 1 chlorine, 1 chlorine. When you draw it together, you find out that carbon will actually combine with chlorine to give us something like this. Let's take this to the atmosphere. 1, 2, 3, 4, 5, 6, 7. So this is what happened to the other parts. Also, carbon can actually combine with carbon compounds, like it can combine with carbon itself, to form so many other compounds. And that is definitely what brings us so much to hydrocarbons. Carbon combining with itself and just having an addition of hydrogen. That is why we say that hydrocarbons are organic compounds containing carbon and hydrogen only. Now when we come to that, we see something like this. H. Now I want us to note something, that we have this structure, carbon, surrounded by hydrogen. Now, surrounding every carbon atom in bond formation, especially when it has to do with hydrocarbon, must be 4 bonds. That was why I made use of these 4 bonds, combining with 4 different hydrogens to make sure that the bond is formed. Why? Because of these single bonds, these single electrons that are at the atmosphere. Of course, this will tell us that carbon involves in covalent bonding. Covalent bonding, that has to do with sharing of electrons. It has up to 4 electrons in the atmosphere. We cannot transfer. definitely what it needs to do to attain stability or octet state will definitely be what? Sharing. And sharing has to do with covalent bonding between two non-metals. Now, this is carbon surrounded by 4. Now, this is carbon, and as I said earlier, surrounded by 4 hydrogens. Assuming 1 hydrogen, we remove 1 hydrogen from here, and carbon actually combines with this side. So we have something like this, and definitely surrounded by 4 bonds. 1, 2, 3, 4. Now, apart from this formation or this bond formation in carbon, you can still have sometimes can actually combine with other elements for bond formation. Of course, this is covalent bonding. So sometimes if you have something like B here, we have this is actually bromine. Definitely, this will not affect the whole bond formation. The only thing that hydrogen will be removed and bromine actually took place. Also, now sometimes also you can have something like this hydroxyl, or definitely hydroxide. We can have nitrogen. So I just want to bring out the fact that this or other elements can be attached or can bond to carbon when it comes to hydrocarbons. And because of the presence of all of those elements, it actually gives rise to a change of name of those. Now let's look at classifications of hydrocarbons. Hydrocarbons actually can be classified into 2 main types. We have the aliphatic hydrocarbon and we have the aromatic hydrocarbon. Now, aliphatic hydrocarbon is also divided into 2. We have the acyclic and the cyclic. When we talk about acyclic, we are talking about arrangement of carbon or elements. Definitely carbon and hydrogen with the combination of some other elements that can still come in. The arrangement of these elements in an open chain. Now, this is just like a straight chain. You can come in form of a straight chain. We have this is butane. 1, 2. Don't worry, we'll find out how this name came about when we start naming these hydrocarbons. This is actually in a branch form. This is the branch chain. Another one, another carbon at carbon number 2. That's 1, 2, 3, 4. Now another chain from carbon number 2, and that gave us the name 2-methyl-butane. Now this is just the acyclic form of classification of classes of hydrocarbon because they are in open chains. Now definitely dealing with the aliphatic hydrocarbon is also the cyclic hydrocarbon. Now here, here the chains comes together to form rings, and we have the cyclopropane now in a ring form. We can still have something like cyclobutane in a ring form. So instead of being in straight or branches, they can just come together to form cyclo. That is a ring or in a cyclic form. That gives rise to the cyclic form of aliphatic hydrocarbons. Now we look at aromatic hydrocarbons. It's actually a ring. In fact, this is just a major part of hydrocarbon. And when we talk about it, we're talking about benzene and every compound that it forms. We're talking about benzene ring. Whenever you hear anything about aromatic hydrocarbons, we're talking about benzene ring and everything that forms from the benzene. In the sense that this is the benzene ring, of course, this is the double bond here. Sometimes you can see this benzene as this. In this form, it's a zero, like a circle inside it. You see that this form is still the same thing. Or sometimes these double bonds can still swap to give us something like this. So in any case that you see it, benzene ring has to do with aromatic hydrocarbon. Now, from this benzene ring, we can have an attachment of other elements. As I said earlier, this is bromine. Hydroxyl group can just come here. You can have nitrogen here. So all of these things can still come into the benzene ring, and all other compounds that has to do with benzene is aromatic hydrocarbons. I also want us to know that paracetamol actually is actually a branch or came from the benzene ring, and it is an aromatic hydrocarbon, the phenyl. That is by the way. Now look at the simple classification of hydrocarbons: aliphatic, and aromatic. Aromatic has to do with benzene only, and other compounds that still is attached to that is formed with benzene. From aliphatic, we have this acyclic, alkanes, alkynes, and all that. This is the branch one. These are the straight chains. This one is branching. You have the cyclic, that is cycloalkanes. You have the cyclopropanes, cyclobutanes, cyclopentane, cyclohexane, and all that. Now, let's look at some terms related to hydrocarbons. We have the homologous series and the functional groups. Now, before you can name any compound or any organic compound of hydrocarbons, you will definitely know these things that we are going to talk about now. So make sure you study them well. Now, what is a homologous series? A homologous series is actually a setup or a series that shows the relationship between related compounds. Now we talk about alkanes. Alkanes are a different member of the hydrocarbons. Now alkanes, they have so many other members. We have the methane, we have the ethane, propane, pentane, butane, as the case may be. Now they are just homologous series because they are related, and that is why they have the same name. Now, what are some properties definitely of homologous series? Now, every homologous series must have a general formula. For alkanes, the general formula is CnH2n plus 2. For alkenes, CnH2n. For alkynes, CnH2n minus 2, as the case may be. So every homologous series must have a general formula that you can form another one, or maybe you can form the subsequent members of that series from the general formula. Now also, every homologous series also differs, or members of homologous series differs with CH2. Now, I called some of the members of alkanes. We talk about the methane, ethane, butane, propane, and the rest of them. So the difference between butane and propane, that's the last one and the one coming up. The difference between butane, okay, we have the methane, we have the ethane. Let's use this first two. Now, the difference between ethane and methane is simply minus CH2, as the case may be. The difference between the next one, propane, and the one coming up here is still CH2. So all homologous series differ from each other. It just with the difference of CH2, one carbon and two hydrogen. Also, homologous series are prepared the same way. They have similar preparation pattern. They have similar or the same chemical properties. They have the same physical properties, just some slight changes in the structures. Now let's look at functional groups. Functional group is actually a group of atoms, or of atoms, or actually an atom, that determine the chemical or physical properties of organic compounds. Now let's look at this. This is the homologous series. We have the functional groups, the general formula, and these are some of the examples. Now these are alkanes. The first part of the homologous series, we have the alkanes. Now alkanes is actually denoted by straight chains, single bonds, and they have a general formula of CnH2n plus 2. And it says that after getting the first member, the second one you can still get it with the general formula. Then let's try this. Methane is CH4. That's the first alkane group. Now let's see how we can get the next member using this CnH2n plus 2. Now definitely this is one carbon. The next one should be 2 carbon. H2n, the n, number of carbons, and 2 plus 2. We have C2. H 2 times 2 is 4. 4 plus 2 is 6. Now this is just ethane, as the case may be. So for using the general formula of alkanes, you can get the subsequent members of the homologous series of alkanes. Now this is an example of alkane group. We actually used ethane, exactly what we got here. Making it of 2 carbon and 6 hydrogen. 1, 2, 3, 4, 5, 6. And don't forget, surrounding every carbon atom must be 4 bonds. And surrounding every hydrogen atom must be 1 bond. Why? Because hydrogen is 1, and if you draw the configuration, it will just have one electron. So that's one electron in the atmosphere made it easy for it to share or even transfer electron. It can even involve in electrochemical, in an ionic bond or electrovalent bonding. Now we have the alkenes. Alkenes actually is denoted with double bond. There must be double bond between two carbon atoms. So any structure that you see, and you find that between any of the carbon atoms, two of them, there is actually a presence of double bond. Whatever name or whichever name you get it has to be that of the alkenes. This is the general formula CnH2n. Now try using CnH2n to form other members. You find that this general formula gives other members. We have the ethene as an example, making use of two carbon. Remember the double bond between two carbons and this. Now, I don't know if somebody is asking a question, why is there no other bond here? Since surrounding every carbon atom should be 4 bonds. Now, the presence of this double bond has actually made it to 1, 2, 3, and 4. So because of this double bond, you don't need to have an additional bond again on the carbon atoms. 2 carbon and 4 hydrogen. Now we have the alkynes. Alkynes denoted with the presence of triple bond. Whenever you see triple bond, we are talking about the alkynes. Of course, the general formula CnH2n minus 2. The n can be in form of 2, 3, 4, as the case may be. We have an example. We have the ethyne, making use of 2 carbon atoms, triple bond. Of course, 1, 2, 3 bonds. Definitely, the other bond that carbon still now needs just be 1. So because carbon just needs 1 bond, we just bond with just one hydrogen, making it 2 or C2H2. That's an example of it. That's the ethyne. We have the alkanols. Alkanols are actually gotten from the alkenes, and definitely they have similar general formula, just the difference in their functional groups, and that is just the presence of OH, the hydroxyl group. That's the OH. So definitely from alkanes you can get the alkanols, but there must be a presence of OH. This is an example of it. We have the ethanol as an instance. Of course, this general formula, instead of 2 here, just like the alkanes, we just have a presence of OH, just 1. Now this is an example. We have the ethanol, 1, 2, 3, 4, 5. Remember, single bonds formed from alkanes with the presence of OH. Now let's look at this is actually a table. There are other ones, and that will be your assignment to get other ones. Let's look at finally isomerism. What is isomerism? We talk about hydrocarbons. It's actually the occurrence or the existence of 2 or more compounds with the same molecular formula but different molecular structures. Don't get confused. Molecular formula and molecular structures. They are 2 different things. When we talk about formula, we're just talking about this. As we have this C2H2, this is just a formula. But when we come to something like this, 1, 2, 3, this is what? A structure. Now let's look at the types of isomerism. We have 2 main types of isomerism. We have the structural isomerism and the stereoisomerism. Now coming from the structural isomerism, of course the structure, I should tell you, it has to do with just a slight change in the structure. Now we have the chain, the straight chain or the branch chain isomerism, and we also have the positional isomerism. Now when we talk about the branch or the straight chain isomerism, we're talking about something like this. Assuming we have this, let's show that of structural isomerism. Assuming we have something like, let's make it of an alkane. Let's use the propane. 3 carbon. 1, 2, 3. 1, 2, 3. And we have this. Now this is just a straight chain. Now this particular propane can still become in another form. with just two carbon. Now this part of the structure can just come to any of the parts. Let's make it of the first one. And then we complete the bonding surrounding it with 4 bonds. Now, this particular thing that we do here is exactly the same thing with this one. Just that there was just a change in the position of this particular part by the second. And then it just came down to the first carbon. So this is just the propane. And just the name of this one will be 1-methyl ethane. Now, this is an example of a stretch of branch chain isomerism. When we talk about positional isomerism, we just have to do it. Let's still use the same one. But in this case, it will no longer be this particular structure. We have the same structure, but here, let's have CH3. Now, this will be the first one. Then, if we have something like this again, maybe here, we have this. Now, you find out that the position of the CH3 has changed. In the first structure it was here, it was in the second carbon, whereas in the second structure it was in the third carbon. That is for positional isomerism, just a change in position of some elements or some compounds in the structure. And then we have the metamass. It's still like positional isomerism. Then we also have the stereoisomerism. Just if this particular isomerism takes place in only alkenes, where there is presence of double bond, it can still take place in that of alkynes, but most times in alkenes, presence of double bonds. It's just a swap in the presence of the attachments. Assume we have CH3 here, and we have bromine here. We can just have CH3, let's use bromine, and then CH3. And then here, we have CH3, we also have CH3. These things are substituents. We can have bromine and bromine. So, just a change in the substituents. This one will not have this slant form, whereas this one will just be the same form. That is what we talk about stereoisomerism. This actually takes place in when we talk about D, glucose, and L and all that, lavo and testo, and all that. Now, this is all about hydrocarbons. For your assignments, I actually gave us this particular table. There are more. We have the amides, we have the alkanoids, we have the amides, and all of that. So get the rest of the homologous series. Put it in this particular table. The others, there are up to 10 of them, and I just picked 4. So get other 6 ones and submit to me through my WhatsApp number 090 799 617 88. Make sure you do your assignment and submit to me, and if you have any question, ask me via WhatsApp. Thank you.